Okay. I don't know how I'm going to do with these lights. I should put on sunglasses, but I'll try to avoid that. Okay, thinking for programmers. Why think? I'll think of it in a minute. It helps us to do most things. For example, we started out hunting saber-toothed tigers, we build houses, and we write programs. And thinking helps us do all those things. So when should you think? Well, if you're hunting a saber-toothed tiger, you should be thinking before you leave the cave. When you've got a tiger charging down at you, not a good time to start thinking about it. Building a house. Before you begin construction, you don't want to be in the middle of putting a wall up or something and say, gee, what am I doing here? And similarly, writing a program, you should think before you write any code. So how should you think? One of my favorite quotes from the cartoonist Gwendolyn, writing is nature's way of letting you know how sloppy your thinking is. To think, you have to write. If you're thinking without writing, you only think you're thinking. You know, it's very easy to fool yourself. We're all very good at fooling ourselves. You've got to write to know what you're really doing. Okay, what to write? If you're hunting a saber-toothed tiger, sorry, writing hadn't been invented, which means that hunting saber-toothed tigers was a very dangerous activity. Building a house. You think, what you write when you're thinking about building a house is a blueprint. Well, you draw blueprints, you don't write them, but it's the blueprint that you're putting down that concretizes your thoughts. Writing a program. Again, you write a blueprint before you start coding, except in programs, we don't call them blueprints, we call them specifications. Now, specifications, if I say the word specifications, panic. Don't panic. This indeed is a blueprint. You know, blueprints can be really complicated, hard to deal with. But this is also a blueprint. Blueprints come in all sizes and shapes. In fact, there are a whole spectrum of blueprints. If you're building a bridge, then you'll need a very detailed, very complete set of blueprints. If you're building a tool shed, your blueprint can pretty much just be a rough sketch. If you're building a small house, well, you're somewhere in the middle. What I might call an ordinary blueprint. And similarly, there's a spectrum of specifications. On one end, there are formal specifications written in precise languages that can be read by a computer. And the other end, there are simple prose specifications, a couple of lines or so. And in the middle is what I call mathematical prose. It's a kind of precise prose that mathematicians write when they're doing mathematics. So most code is really simple. You take this batch of bits here and you move them over there, and it hardly needs much thinking. And for that, simple prose, a couple of lines, is good enough. Some code is subtle. It requires more thought. You don't want to just dive right in coding it. And some code is really complex or really subtle and hard to get right, or maybe very critical. And things are complex and subtle, especially when you have concurrent or distributed systems. And those things that it's either really important to get right or really hard to get right, we need to have tools to be able to check our thinking. And for that, we need a formal specification. So, how do you write a spec? Well, writing requires thinking. It's a little bit circular here. To think, you have to write. To write, know how to write, you have to know how to think. Well, How do we think about, not going to be talking about hunting saber-toothed tigers, I'll be talking about programs. So how do we think about programs? And the way you should think about programs, you should think like a scientist, because that's a really successful way of thinking. It's brought us all the things we come to take for granted in modern life. And what science does, science makes mathematical models of reality. For example, what may be the first science is astronomy. And there's the reality of astronomy. Astronomy started dealing with the planets. Well, planets are complicated things. They got mountains, oceans, tides, weather, all that sort of stuff. But the model that astronomers used, at least when they started, to start figuring out the motion of the planets, is to represent the planet as a point mass with just position and momentum. It's a lot simpler than the reality. Computer science. The reality consists of digital systems. Maybe a digital system could be a processor chip, a game console, a computer executing a program, or a cell phone, or lots and lots of stuff. Doesn't make much difference which of them you're building. The basic ideas are the same, but I'm going to talk about a computer executing a program as the reality that I'm considering here, but I think that's probably what the reality that concerns most of you or many of you. But it just applies equally well if you're building a chip or a game console. There are lots of models that have been used. Turing machines, partially ordered sets of events. I could list them. Most of them probably not mean much to people here. But there are two models of reality that I find to be the most useful ones, especially when writing programs. The first is functions, and the second is sequences of states. So functions. And with functions, you model a program as a function that maps inputs to outputs. So what's a function? Well, in mathematics, a function is a set of ordered pairs. For example, the square function on natural numbers. It consists of this set of ordered pairs. So for example, that element 2, 4 in the set means that the function square applied to the value 2 equals the value 4. So we say that the domain of square is the set of all of the first elements in those sets of pairs, the numbers 0, 1, 2, or 3, called the set of natural numbers, which I write as nat. And to specify a function, we write two things. We specify its domain. So we say the domain of square is equal to nat. And then we specify the value of the square of the function on an arbitrary element in its domain. So for example, square applied to an arbitrary element x in its domain is equal to x squared, of course. And so that's how you specify a function. Now, programming languages, a lot of programming languages have things that they call functions. They are not the same as functions in mathematics. I don't know, I have a vague idea of what those things called functions are in various programming languages, but they're a lot more complicated than functions in ordinary math. Functions in ordinary math are really simple. They're just sets of ordered pairs. Now, the function model is very useful, but it has its limitations. What it does is it specifies what a program does, what value it produces for each input value, but it doesn't tell you how it computes it. For example, quicksort and bubble sort, two sorting algorithms, that compute the same function. The function is, your input is a list, the output is that same list sorted. But quicksort and bubble sort are two very different algorithms, very different ways of computing, of doing the sorting. Also, some programs don't just map inputs and outputs. Some programs run forever. Well, you know, like your operating system. Well, we know that it doesn't run forever. It will eventually crash or run out of memory or do something. But it's useful mathematical abstraction to pretend that they're running forever rather than that they're going to stop at some time. Things like operating systems. Now, I'll describe the standard behavioral model is that a program execution is represented by a behavior. So what's a behavior? A behavior is a sequence of states. So what's a state? A state is an assignment of values to variables. And the program is modeled by a set of behaviors. The behaviors representing the possible executions of the program. An example, I'll take Euclid's algorithm. An algorithm is an abstract program. So what the algorithm does, it computes the greatest common divisor of two numbers, call them m and n. Does it by initialize x, it uses two variables, x and y. Initializes x to m and y to n. And keep subtracting the smaller of x and y from the larger one. And you stop when x equals y. And when x equals y, that value of x and y is the GCD of the two numbers. So if m is equal to 12 and n is equal to 18, there exists one possible behavior, which is this behavior. Starting in this state, with x equals 12, remember a state is an assignment of values to variables. It then goes to this state, and then to this state, and it stops when x equals y. So how do we describe a set of behaviors? We do it with two things. First, we describe the set of all possible initial states. And we describe a next state relation, which describes for any particular state all the possible next states for that you can reach from that state. For infinite behaviors, we also need to talk about fairness, and I don't have time to talk about it, so I'm going to ignore fairness and just look at these two things, the initial state, the set of initial states, and the next state relation, which turn out to be the most important things when writing a specification. So what language should we use to describe them? Well, we don't need no stinking language. We can use mathematics to describe them. So the set of initial states, they're described by a formula. So for example, Euclid's algorithm, for particular values m and n, there's only one state. It has x equals m and y equals n. So that state is described by this simple formula. And that describes the only possible initial state. The next state relation is also described by a formula. A formula describes the relation between the current state and the next state. And we'll write it by using unprimed variables to describe the values of variables in the current state, and primed variables to describe the values in the next state. So for Euclid's algorithm, y, the other one, y is bigger than x, and the formula says either do one thing or another, and or is represented by disjunction in mathematics. So in the case x is greater than y, you get the new value of x by subtracting the smaller from the larger. So the new value of x is equal to x minus y. And y is left unchanged, so its new value equals its current value. Similarly, if y is greater than x, then you change y by subtracting x from it, and you leave x unchanged. And so that's the formula that describes the next state relation. So let's see how that works. How do those two formulas describe the behaviors? Well, we'll do it for the special case of m equals 12 and n equals 18. Initial predicate says x equals m and y equals n. Well, we substitute 12 for m and 18 for n, and we see that tells us that there's only one possible initial state, one that assigns 12 to x and 18 to y. So to find the next state, we have to go to look at the next state relation. And the current state, we know that x equals 12 and y equals 18. So we substitute those values for x and y, and then we just do a little calculation. Well, 12 greater than 18 is false. False and anything is false. So this first part of the formula is equal to false. False or anything is equal to that thing. And 18 greater than 12 is true. So this formula simplifies to this part, y prime equals 18 minus 12, x prime equals 12. So it tells us that the possible next state is y prime, y in the new state equals 6, and x prime, x in the new state equals 12. So that tells us what the next state is. And since there's only one behavior for this particular algorithm, then the next state, there has to be a unique next state. And okay, to go from there, we do the same thing. We substitute the current values of x and y into the formula. This time, the bottom disjunct is false. The top one is true. And it tells us that the new value of x is 12 minus 6, or 6, and the new value of y is 6. Okay, we keep going. We now substitute 6 for x and 6 for y, and we see that both parts of this formula equals false, and false or false equals false. So the entire next state relation equals false, and there's no values of x prime and y prime which make false equal to true. Therefore, there is no next state, which means that the behavior stops. So that shows how the initial predicate and the next state relation determine if there are any values, which means that Euclid's algorithm is deterministic. To model non-determinism, all we do is we allow multiple next states for a current state, which means that the formula allows multiple different assignments to the prime variables that makes next true for the same assignment of values to the unprime variables. I don't have time to write an example, but remember we have the OR, so you can just take the OR of any formula with any other formula, and you can get two different ways, formulas that can be satisfied by the new values, by the prime values of the prime variables. Okay, what about formal specs? Well, remember, we need them only to apply tools. They require a formal language. The language that I use is called TLA+. So this specification, remember, we have these two formulas, which you might call init and next. Well, the specification becomes this, where that fuddy symbol means that just defining init to mean equal this formula and defining next to be this formula. Add some declarations of these symbols, m and n and x and y. Add some boilerplate where this extends the integers. This imports definitions of things like greater than and minus, and a little boilerplate, and that's the specification. And this is what you actually type in ASCII. You can see it. It's pretty easy to read. So what can you do with this spec? Well, you can model check it. Model checking means that you conceptually find all possible executions, all possible behaviors satisfy the specification, and you can check that they satisfy desired properties. You can write formal correctness proofs and check those proofs mechanically. But this is all nice, but we know that math works only for toy examples. To model real systems, you need a real language with types, procedures, objects, etc. Wrong. TLA plus is used, specifies systems exactly the way I just described for Euclid's algorithm, except the specifications are larger, hundreds of lines rather than half a dozen lines. People use them. Here are how TLA plus is being used at Amazon as we speak, or as I spoke. This is things that have already been done. It's an incomplete list. This is the information that I got from Amazon about in the fall. And notice, found 2 design bugs, 1 design bug, 3 design bugs. These are real distributed systems. Now, you may say, oh, 2 bugs, 3 bugs, big deal. There are hundreds of bugs. Well, these aren't your average coding errors. These are fundamental design bugs, not just coding bugs. These bugs are serious. They're often impossible to find by testing. That if they had not written these specifications, those bugs would have made it into the production code. And those were serious bugs. They could have caused loss of user data. That's the kind of problem they were worried about. TLA plus has seen some various uses at Microsoft. One example that Chuck Thacker, hardware designer in our lab, told me about was the Xbox 360 memory system. Chuck had a summer intern, and he had the intern write a formal TLA plus specification for the Xbox's memory system. And in the course of that, he discovered a bug in this memory specification, just in the act of writing the spec before he even got to doing any checking of it. Chuck sent that sent that bug to IBM, who were the builders of the chip, and said, it can reach this state. And they looked at it and they said, no, that's impossible. You're wrong. So Chuck sent them a scenario that would produce that state, sent it off to them. 2 weeks later, presumably after they had scratched their heads long enough, they reported that, yes, that was a bug in their design. That bug would not have been caught by their tests. Had the Xbox 360 been shipped with that bug, every Xbox would have frozen after 4 hours of use. These are the kinds of bugs that you can catch only with specifications. You can learn about TLA plus on the web. Today, what I'm going to be talking about is informal specs, the kind that you'll probably be much more likely to be writing most of the time. I'll start with an example. This is the pretty printer for the TLA plus language. Taking the examples from code that I've written. And I don't write an awful lot of code, so I don't have an awful lot of examples at my disposal. But I think this is a nice one. Here's the typical input that somebody might write. Now, if you just naively substituted symbols for the ASCII characters, you'd get something that looks like this. But the user probably wrote these alignments because he wanted those symbols to be aligned. And so the right output should look something like this. On the other hand, suppose the input looks like this. Then this would be the naive output. But those alignments are probably just coincidental, and the user probably doesn't want them aligned. So the naive output is, in fact, the right output in this example. Now, there is no precise definition of correct alignment. Correct alignment means doing what the user wants, and there's no way of mathematically specifying what the user wants. So, if we can't specify correctness, specification is useless, right? Wrong. Not knowing what a program should do doesn't mean there's no point thinking. It means we have to think even harder before we start coding, which means that a specification is even more important. So what did I do? Well, let's look at my Java code. Place to put a specification, at least an informal specification, is as comments inside of your code. And you look at my code, you'll see lots of specifications in the comments. So here's the code, and it says here, there are 6 kinds of alignments illustrated by the following example. And there's an example, and then it says, here are the descriptions of those 6 different kinds of alignments. And a bunch of descriptions. Here is one of those types of alignment. It says left comment alignment. If T is a left comment token, then it is left comment aligned with its covering token. Well, that doesn't mean much to you, but what does it mean? Well, what's left comment token? You go back up in the spec and you'll see a left comment is a comment that is the first token on its line, but not the last token on its line. And so on for 215 lines. This is what I mean by a mathematical prose specification. It consists of 6 rules plus explanation. Those are comments in the specification. So why did I write this spec? The reason I wrote it is that it's a lot easier to understand and debug 6 rules than the 850 lines of code that those rules eventually turned into. Now, I did a lot of debugging of the rules. Now, how did I debug it if wasn't a formal specification? Well, what I did is I added debugging code that simply reported what rules were being used whenever it produced output. So I could run tests and see what it did, and if it screwed up, I can see what rules it was using that caused it to screw up. And did that enough to debug these rules. Now, the few bugs that I made in implementing the rules were very easy to catch. But had I just written the code, it would have taken me much, much longer to try to debug it and figure out what was going on. And I could not possibly have produced code that did as good a job as it does. It does a pretty damn good job, as you would find if you started using it. Not perfect, but nothing can be perfect because no set of rules can do exactly what every user wants, not even exactly what I want all the time. But it does a pretty good job. About 10 years later, I enhanced the program to pre-print PlusCal code in the comments. I'll mention later what PlusCal is, but it's stuff that goes into the comments in the TLA Plus specification. Now, it was a lot easier to modify a 6-rule spec than 850 lines of code. What it required was to change the spec. After a fair amount of thought, that I just had to add 1 rule. And in order to implement that new rule, I had to make these changes to the code. Not very big changes. Had I not had this spec, I probably would have had to just start from scratch and rewrite the code all over again. So why didn't I write a formal spec? Well, first of all, getting it right isn't that important. No bridge is going to collapse because the specification isn't pretty printed quite right. Didn't have to work on all corner cases. Nobody's data was going to be lost because something wasn't aligned quite right in the specification that he wrote. And also, there were no tools that could have helped me. So what's typical about this spec? What's typical about it is that it's at a higher level than the code. It's really important. You should be thinking about how to solve the problem, the algorithm, what's going to happen, not how it gets coded. Coding is the easy part. It could have been implemented in any language. And no method or tool for writing better code would have helped to write the spec. The coding was the easy part. The hard part was the thinking of what the code was supposed to do. And no method, no matter how wonderful your method is for writing code, it would not have made the spec unnecessary. And the spec says nothing about how to write the code. It's completely orthogonal to the code. You write a spec to help you think about the problem before you think about the code. What's not typical about this spec is that, first of all, it's quite subtle, the set of rules. 95, as I said, most of the code that you write requires much less thought, and specs that are shorter and simpler will suffice. The other thing that is unusual about it, it's a set of rules. A set of rules or requirements or axioms is usually a bad way to write a spec, because it's hard to understand the consequences of a set of rules. But the fact that this turned out to be the right way, or the good way of writing the specification of this problem, is closely related to the inability to mathematically formalize what correctness means. The best way to write a functional spec, which is what this is usually to write a function. You can then check that the function implements any of those desired requirements. But this was a special case. So specifying how to compute a function. Specifying what the pretty printer should do was hard. Figuring out how to implement it was easy. On the other hand, specifying what a sorting program is supposed to do is pretty easy. We all know what sorting means. Not quite trivial. There are corner cases in that too, but it's pretty easy. On the other hand, figuring out how to implement it efficiently is really hard, at least if you haven't taken some course or read some textbook on all the various sorting algorithms around. It requires thinking, which means writing a specification. Example I'll use is quicksort, example of specifying how something is computed. How many of you know what quicksort is or have seen quicksort? Most of you, good. So as you know, it's a divide and conquer algorithm for sorting an array, say an element of array. And for simplicity, I'll assume it's an array of numbers. And it uses a partition procedure, which has two arguments, low and high. And what the procedure does is it chooses a pivot in this interval, and then it permutes this range of the array, the elements of this range of the array, to make all the elements up to the pivot element less than or equal to all of the elements to the right of the pivot element, and it returns pivot. And for this example, I don't care how this procedure is implemented. I'll just assume that we have procedure. So let's specify quicksort and do it in pseudocode, which is a typical way. Here's a sort of a pseudocode description of what the partition procedure does. It picks a pivot in low and high, and it permutes A low and A high to make blah, 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 just like I told you, and returns pivot. And then there's this recursive procedure, which you can read it. It takes two arguments, and if low is less than high, then it calls the partition procedure on that interval, and then it calls itself recursively on the two subintervals determined by the partition. And then the main program just calls QS on the entire array. You've seen this before, so notice it's informal, no syntax, no declarations. It's a pretty nice spec. It's easy to understand. But is it really quicksort? It's the way quicksort is almost always described. But recursion is not a fundamental part of quicksort. Remember I said quicksort is a divide and conquer algorithm. And recursion is just one way of implementing divide and conquer. And in fact, it's probably not the best way of doing it. if you want to execute quicksort on a multiprocessor. So here's a problem. Write a non-recursive version of quicksort. Don't have time to let you scratch your head and puzzle over this. But I will tell you that almost no one can do it in 10 minutes. What they try to do is compile the recursive version, into explicit stack and stuff like that. And almost nobody can do it on their feet in 10 minutes and get it right. But here is what I consider the solution, the way of writing quicksort. You do is maintain a set U of index ranges on which partition needs to be called. Initially, U is a set just consisting of the entire region, which I'll represent by the ordered pair of its endpoint, 0 to n minus 1. Now, we could write this in pseudocode, but it's better to just simply write the initial predicate and the next state relation directly. So here's the initial predicate. Initially, A is any array of numbers of length n, and U has this value. And again, this is an informal way of writing the specification. It's an informal way of writing a mathematical formula. Now, before I write next, let me make a definition. I'll define partitions of B pivot low high. It's basically the set of all arrays that can be obtained starting from when the initial array has the value B, that could be arranged by calling the partition procedure and having it return a value pivot, assuming pivot is between low and high. So it's the set of arrays obtained from B by permuting B low to B high such that the array elements to the left of pivot are less than or equal to the array elements to the right of pivot. I could write this as a mathematical formula or more precisely, but I won't bother doing it. Now, next is going to be a relation between, there are two variables, A and U. It's going to be a relation between the old values of A and U, the starting values, and the new values, A prime and U prime. So let's write it. Well, we want to stop if U is empty. When U is empty, we're through. So we say we only do this if U is not equal to the empty set. And then what we do is we pick any pair B and T in U. And that's bottom and top of the partition, of the subarray that we want to pick any pair BT in U, any range in which we need to call partition. If B is not equal to T, then we pick any pivot P in this subinterval, and then let A prime, the new value of A, be any element in this set partitions of that I just defined before. So in other words, A prime is any value that you can get by calling the partition procedure on this interval, B to T, in which it would return a value, a pivot point P. And then U prime, the new value of U, is the old value of U, except we removed the interval BT, and then add the subintervals, the two subintervals, from B to the pivot and from pivot plus 1 to T. Otherwise, there's nothing to do. B is equal to T. Then we just let A prime equals A, and we just remove that interval BT from U. So here's our next state relation. So why can almost no one find this version of quicksort? It's because people's minds are stuck in code. You say quicksort, they think code, and they want to code it in a programming language. And you can't write a next state a relation like this in any conventional programming language. People are so used to thinking in the code level that they can't think at a higher level. Now, I wrote this as a very informal formula, but it's easy to write this as a precise mathematical formula. First of all, pick any arbitrary value really means to say this is going to be true if there exists such a value. So pick an arbitrary value is really existential quantification. I hope you've all seen existential quantification somewhere in your schooling. Similarly here, this is just existential quantification. Then sometimes pick any element is even simpler than that. Let A prime be any element of this set, just A prime an element of that set. And similarly, these relations, U with BT removed and this added are easily written with normal set notation. And so this is, in fact, a TLA plus formula. You can type this into your TLA plus spec. And you can write the similar formula for the initial predicate, and we can let the model checker check whether it works. Now, if you prefer pseudocode, in addition to TLA plus, there's a language called PlusCal, which looks like a toy programming language. And the algorithm appears in a comment inside of a TLA plus module. But a PlusCal algorithm is much more expressive. PlusCal is much more expressive than any programming language because an expression can be any TLA plus expression, which means it can be any formula of mathematics. The language also has constructs for nondeterminism. And it gets compiled into an easy-to-understand TLA plus specification, initial predicate, next state relation. So if you want to figure out what the PlusCal code actually means, you look at its translation. And engineers actually do that. I mean, some engineers prefer using PlusCal, and they use that instead of using TLA plus directly. And when they don't understand something, they look at the TLA plus translation and see what it means. And again, you can apply, since you have the TLA plus translation, you can apply the TLA plus tools, the model checker, and you can write proofs. What about programs that run forever? I've been talking about programs that compute a function. Programs that run forever usually involve concurrency. There are things like operating systems and distributed systems. Few people can get them right by just thinking and writing. I'm not one of them. Maybe once upon a time I used to be, but not anymore. We need tools to check what we do. And if you need to use tools for checking a system, a concurrent system, I think TLA plus and PlusCal are the best languages and tool sets around for most of those applications. Of course, I'm prejudiced. But people at Amazon at least agree with me. Okay, what about the other 95%? As I said, most code is really simple. So here's a typical specification that I write for a Java class. It says resource file reader returns blah, blah, blah. You can read it faster than I can say it. Very simple. Why did I write that spec? I wrote it to be sure that I knew what the code should do before I wrote the spec, before I wrote the code. Again, thinking before writing. Thinking before coding. And thinking means writing. And if the thinking is very simple, what you write will be very simple. Without writing a spec, again, I only thought I knew what it should do. And later, when I wanted to use that method, I didn't have to read the code to know what it did. I just read the specification. And that's a general rule of specifying what code does. The spec should say everything that you need to know in order to use the code. You shouldn't have to read the code in order to use it. Now, in this case, how the code worked was too simple to require a spec. As I said, most stuff is really trivial. So, what programmers should know about thinking? What everyone should know about thinking. Everyone thinks they think. But if you don't write down your thoughts, you're fooling yourself. What programmers should know about thinking is that you should think before you code, which means you should write before you code, which means you should write a spec before you code. So what code should you specify? Well, first of all, any piece of code that someone else might want to use or modify, you should have a specification of what it should do. And that includes you in a month when you've forgotten what this piece of code you've written does. Now, that piece of code could be an entire program or system. It could be a class. It could be a method. It could even be a particularly tricky piece of code inside of a method. You're writing the code. You know what's hard, what's tricky, what needs thought. What should you specify about the code? Well, what it does. Everything that's needed in order to use it. And possibly how it does it. If how it does it is tricky, or if you need to think about how it should do it. You can call that an algorithm. You can call it a high-level design. They're pretty much just different words for the same thing. Now, how should you think about or specify the code? Above the code level. That's really important, not to get bogged down in the code. In terms of states and behaviors, states, if you're describing it functionally, you describe the output state as a function of the input state, as sequences of states, as behaviors, if it's something that has to be described in terms of behaviors. You should think mathematically, as rigorously and as formally as is necessary. The easier something it is, the more informal you can be. The harder it is, the more formal you have to be. And if it's sufficiently hard or sufficiently important, you need to write a formal spec. You might use it with pseudocode or PlusCal for specifying how. But what about the code? The question is, how do you've got this wonderful spec. How do you connect it to the code? Well, if you think that it's a waste of time to write a spec because you can't generate code from it, remember, architects can't generate a building automatically from a blueprint. But architects believe that it's still worth writing blueprints. And just think about why they believe that. Now, what you should write are comments that connect the mathematical concepts with their implementation. The mathematical concept is a state with variables, so there are state variables. Now there'll be variables, things in your code that correspond to those mathematical variables, and you should describe how the code corresponds to the mathematics. For example, the mathematical concept is a graph. The implementation is some array of node objects and link objects and stuff, and there should be comments explaining how these objects represent a graph. Well, what about coding? Nothing I have said implies anything about how you should code. You still have to think while you code. Thinking means writing, but what you write while you're coding is code. And I have nothing to say about how you should code. Use any programming language you want. Use any methodology you want. no programming language, no methodology obviates the need for specification. It's a separate specification, is a separate task from coding. You're still not going to have to test and debug. The specification can catch high-level mistakes, fundamental design errors, but it's not going to catch coding errors. Your coding is coding, and you can make errors coding. Fortunately, there are a lot of tools around for catching coding errors. But writing the specs is an additional step. It may save you time by catching errors early when they're easier to correct. But I'm not going to guarantee that it's going to save you time. It's always easier to do something sloppier and poorly and get it done faster. But writing specs will improve your programming so you write better programs. You may still be able to write really crappy programs faster without writing specs. But I don't want to use your programs if that's what the kind of programs you're writing. So why are programmers reluctant to write specs? Well, writing is hard. Why is writing hard? Writing requires thinking, and thinking is hard. It's easier to think you're thinking. Writing is like running. The less you do it, the slower you are. You have to strengthen your writing muscles. So you have to write. And no matter what you're writing email, be careful to write your email precisely. You write a precise piece of email that the reader can't misunderstand. Then you're teaching yourself to write specifications. It takes practice. It's easier to find an excuse not to. Well, what if the spec is wrong? Maybe you made a mistake in the spec. Maybe the requirements change when an enhancement is needed. And the code will have to be changed, maybe even before the program is finished. This eventually happens to all useful programs. If a program is useful, somebody's going to want it to do something more, and you're going to have to change it. In an ideal world, you would write a new spec and rewrite the code completely. In real life, you know that doesn't happen. The code gets patched, and maybe, if we're lucky, the spec gets updated. So if this is inevitable, why do we write the specs? Two reasons. First of all, whoever has to modify the code will be grateful for every word or formula of spec that you write. I know. Remember my example of that pretty printer. I was very glad that I had written that spec rather than having to completely rewrite the code from scratch. And so that's why you should update the spec when you change the code. Second reason, every time code is patched, it becomes a little uglier, harder to understand, harder to maintain, bugs get introduced. If you don't start with a spec, every piece of code you write is a patch, which means the program starts out from day one being ugly, hard to understand, and hard to maintain. The words of Dwight Eisenhower, "No battle was ever won according to plan, but no battle was ever won without one." So thinking doesn't guarantee that you won't make mistakes. But believe me, not thinking guarantees that you will. Thank you. I guess there are time for a few questions. Can you go down to, I think, there are mics I think we should be using.
I guess some of us might model like concurrent systems with like UML.
I'm sorry, it's hard to hear. Let's give people a couple of minutes to exit. Well, okay, yeah, you tell me the question, I'll repeat it.
So I guess like sometimes people use things like UML to model concurrent systems. It wasn't clear to me how to always convert that into the
Okay, the question is, there are people use UML to, things like UML to model programs, but it's not clear how to translate them into sequences of states. For concurrency, if you cannot translate them into sequences of states, it means you don't understand them, and it may mean that there's nothing there. You know, there are lots of people selling snake oil, doing things, drawing boxes and arrows that make you feel good but ultimately have no real meaning. If something is really meaningful, you should be able to express it in mathematics, which means you should be able to express it in terms of an initial predicate and a next state relation. And if you can't, it's not going to help you solve your problems in concurrency. Now, I don't know UML, so I can't tell you, Can the next state be a union of a bunch of states? The next state can have lots of variables. And some method may separate into distinct pieces the part of the next state relation that tells you how the different variables are being changed. But it's really important that you understand them in terms of a single state. Because if they hide, because thinking the right way to think about distributed systems, and I've been doing it for 40 years, is in terms of the state of the system. Okay, someone else?
Yes. I'd like to thank you for all your work on distributed systems over the years. I wanted to get your thoughts on new protocols like Raft, which are supposed to be equivalent to Paxos as far as basic functionality and keeping distributed consensus, but are more understandable by us poor human beings.
If they've got something that works, it's more understandable, that's great. Just make sure that understanding means precise understanding. And make sure that it doesn't seem simpler because somebody has just given a sloppier, more hand-waving description. Compare equivalently formal descriptions of the different algorithms to decide which is really simpler. Okay, but that, I don't, I know about Raft. I haven't looked at it, so can't say anything about it. Questions?
Is agile software development an excuse for not thinking?
To the extent that it is, it's a bad thing. But as I said, you should be thinking before you're coding, and agile programming is a way of coding, not a way of thinking. Okay, thank you.